Hello, and welcome to our demonstration of the AqueCool 2.0. This is our ESET 419 Senior Capstone Project, and we are Team AqueDuct. As a brief introduction, I am Adrian Federley, the project manager. We also have Christian Velas, the hardware engineer, Chance Grunwald, our systems integrator, and Prashant Subedi, the software engineer. Our advisor is Dr. Jiyoung-hee Kim, and our sponsor is Advanced Ambulatory Inc., or AAI. The problem is based around recovery and cold therapy options. Single-use chemical cold packs and ice packs are both reliant on time, and some are less reusable than others. The AqueCool device currently pumps and cools water at 50 degrees Fahrenheit through a wearable bladder for use after facial, aesthetic, and reconstructive surgeries. Many of the problems on the AqueCool revolve around its increasing age and the lack of replacement parts in service. Our solution is a complete redesign in the AqueCool 2.0. What does it do? Well, it'll do the exact same thing as before, which is 50 degrees Fahrenheit pumped through a wearable bladder. The only difference is this time it will do so with newer technology and device diagnostics. This way, service technicians can know if there's an error with the device. Let's see how far along we've gotten in our test stand. Here you can see our test stand setup. On the left of the wood structure at the top, we can see our reservoir, as well as just below that, our ball and tube analog flow meter. Behind that, we have our DDC pump, and we can see our fan and heatsink clearly in the top center. All of this is powered by a 3 to 500 watt, 12 volt medical grade power supply, and we have a thermometer that is connected to the cold plate that is full of water that will give us accurate temperature readings. Let's have a look at the time lapse of the cooling ability of this test stand.
This is our functional block diagram. In the top right of the diagram, we have the main water loop used to treat skin areas. The water will be pumped to the cold plate to be cooled by the thermoelectric couplings. The heat will be transferred by the copper transfer plate to the heat sinks, which are air-cooled by fans. The control PCB is where the signal processing, such as analog to digital conversion and power distribution, occurs. The temperature and voltage sensors, along with the flow meter data, will be sent to the STM32 microcontroller to maintain water temperature of 50 degrees Fahrenheit. PC software will communicate with the control PCB via UART. We chose a 12 volt DDC pump because of its high pressure performance and ability to maintain our desired flow rate. We used 4 6-amp thermoelectric couplings in order to cool the water fast enough and to maintain the temperature of the water. We chose to use an air cooling system using 2 CPU air coolers to handle the 2 separate cooling blocks. And lastly, we will be using the STM32F303 microcontroller because of its small design, USB functionality, and ability to be powered with 12 volts.
Okay, so we have our software approach. We need our software to be able to operate and control different hardware components that we have used for this device. We'll use STM32Cube IDE, which is a free development tool and a part of STM32 Cube software ecosystem. It is a free and has a graphical selection of pinouts and supports CC++. We'll also use STM32 HAL library to create our initialization code and control the GPIOs, UART, and other peripherals. Till now, we have verified the use of STM32 Cube IDE and tested the functionalities of ADC and other GPIO ports. Okay, so next is the software flowchart. So here in our main code, we have whenever the main switch is on, it will initialize the variables and turn on all the sensors and components. We have a LED to show the as an indicator. Then we have a diagnostic mode to send and store diagnostic data to view it later whenever it's connected to a PC. Our device, can you go to the next slide? Okay, so this is our code for the changing the temperature and the voltage for the peltier, our device should be able to cool the water at 50 Fahrenheit with 2 degrees of tolerance. For that, we will use a temperature sensor to increase and decrease the duty cycle of the peltier.
One of the main challenges for our product is being able to create a diagnostic system for our device that is easily able to troubleshoot our product during maintenance. The challenges with creating this diagnostic device is creating a current sensing circuit under high current, as well as being able to connect and send our diagnostic to another device for maintenance. Another challenge with our device is being able to deal with high external heat loads of the user of the product. Humans create a lot more heat than it may seem, and when dealing with the heating troubles that introducing a heat source to the system could cause, we needed to be sure we had proper cooling ability in our system. In this overview, we've seen how we are transitioning from the old device to our new design that is much more efficient and much more maintainable, and will be a much easier user experience. As well, we've looked at our components that we're going to be using for our design, and we've seen how they will be implemented and how they are working. We've also taken a look at the software flowchart in our design and how we are implementing both the code in our microcontroller in our device as well as the code on our PC software. Finally, we have looked at some of the challenges that we are working to overcome in our design. Thank you.